Okay, so we'll go ahead and get the last of the lectures finished off here, and then we'll have lots of question and answers in class this week. We want to finish off our nomenclature, so this slide is nice because it gives us everything. The big new addition here is going to be adding the alcohol functional group. The alcohols are just going to change the ending to an OL ending. We won't have to worry about the hydroxy because that is only used when you have something of higher priority. And at this point, you guys don't know anything higher priority than an alcohol. So if you see an alcohol, switch the ending to an OL. The rest of the rules, pretty much the same. So let's hit some practice problems with the alcohols. So we haven't ever really done one like this guy, where we've got it all broken down or given the name to the structure. So let's go ahead and attempt this. Number one, got the OL, so we have an alcohol. So I'd identify that. It'd be nice to know where that alcohol was attached, so we could slowly work our way back through. And yeah, I do see an ene, but that's yet another functional group. So where I will go is with the cyclohex. So I know I need a, whoops, not an eraser, a cyclohex structure. So 6 carbons all arranged in a circle. The alcohol will by definition be at position 1, and then we can go back with the rest of the name. At position 2, we have an ene, so we're looking at a double bond out over here, and I decided to number counterclockwise for some unknown reason. Ultimately it doesn't matter, we just have to do it. And then to begin with, we have a methyl at position 4. There we go. Nice little methyl. You don't have to write CH3, you could just leave it as a normal line. Remember, every point is a carbon. So there we go. The next two are going from the structure to the name. A little bit more challenging. Feel free to pause at any point so that you can try and solve it on your own. I would first identify my longest carbon chain, which is going to be a cyclobute. Because they're all single bonds, I can go with the ane-ish ending. We'll get rid of the E off the end because my functional group is an alcohol. So I'll turn that into an ol. So as far as my substituents go, that alcohol is almost best kind of considered to be part of your main chain. Because it is the highest priority functional group, that carbon where our alcohol is located is by definition carbon number 1. The chlorine, our other substituent, or our only substituent, is going to be at position 2, and so we would have a 2-chlorocyclobutanol. And of course, couldn't make this one super easy. Notice that we have a wedge here, so we have to specify stereochemistry. The chlorine gets the 1. Carbon number 1 will be our 2, 3, and our 4th group is hydrogen. As we connect around, we're running in a clockwise fashion. So we get tag out front 2R, 2-chlorocyclobutanol to put our whole name together. Super exciting. Last practice to take a look at, identify your longest carbon chain. So we've got 1, 2, 3, 4, 5 carbons. So we're looking at a pent. Within that 5 carbon chain we have 2 functional groups, an alkyne and an alcohol. The alcohol takes higher priority, so we're going to include that as part of our group, and that would mean the ending is going to come in as our ol. The reason why I picked this one is we have that alkyne, and really the only way we know to name these things is both based on their ending. So this gets a bit interesting when we try and put together the name. Instead of it being a pentanol, because the an would suggest single bonds, it's going to be a pentyne. We'll drop the E so that we can put in the alcohol. The alcohol will be our lowest number, so it's going to be put at position 1. The alkyne will then follow that 1, 2, 3, and we have pent 3-ine 1-ol. You'll notice as well with this that we don't need the EZ conformations because triple bonds don't give you EZ. Okay, so that's some quick nomenclature practice with your alcohols. Nice and relatively straightforward. Put the alcohols with the lowest substituent number, and we'll change the ending to an ol. If you have other functional groups in there, like an alkene or an alkyne, you will have to do this kind of weird insertion into the very end of the name to include those. Another thing that I want to address as an important aspect with our arrows of organic chemistry. You've seen this table before, and you should read over it just to make sure you're familiar with it. But there is one arrow that I left off of that, which I will remedy in future courses. That arrow is what is known as the retrosynthetic arrow. So that's this arrow shown in between here. It is different from all of the other arrows, which is of course why it's shown slightly differently. What it means is that this, the material on our left was made from the material on the right. So it's kind of odd. It's a backwards reaction, effectively. So what you would go through and do is the same kind of general ideas that you've done with all others. So if we were trying to figure out how to make something, generally we look at our product and think about how we can work backwards to get to some starting reactant. This just happens to be the notational way to write this out. Be careful when looking at this arrow because they could mean very different things. Particularly if we don't change the carbon chain, you might think, how do I make the thing on the right as a product and the thing on the left as a reactant? That would be incorrect. Okay? Your retrosynthesis arrow, we're stating that the thing on the left is our product, the thing on the right is our reactant. And we want to know what steps were involved to go through and get that to occur. Okay? Not a huge issue. We'll see it a little bit more in second semester when you have a larger reaction or reagent background information. So now actually into, I think it's chapter 16, looking at our dienes. This first section is important, which is why I've included it as a separate deal from the Diels-Alder stuff. So what we're going to look at is when we look at alkenes, we did do a couple reactions where there were multiple alkenes in our starting material, but we kind of left those kind of on the back burner and kind of ignored them. When we move up into what's known as a diene, all we're really saying is that there are two alkenes in the same structure. And depending on where those two alkenes are, we could see drastically different results in the overall chemistry. So if we take a look at comparing this through our heat of hydrogenation. So we've talked about this before with our alkenes. Our fully saturated structure, so it's been completely hydrogenated, is our alkane. As soon as we make it unsaturated by adding a double bond, we're going to increase in energy. Okay, so that's why pi bonds react more than alkanes. And we could look at the heat of hydrogenation, which is the energy released to go from the alkene to the alkane. Okay, so this is our heat of hydrogenation. And of course, always fun, because when we look at heat of hydrogenation, we're looking at a change in energy that's going to be equal to our final position minus our reactant position. Whoops. And if you consider that our final position is lower in energy than our reactant position, our heat of hydrogenation will always be negative. Okay, so the more negative the heat of hydrogenation, the higher in energy your starting position, okay, or the higher in energy your alkene was. So where we looked at this before was with alkenes, and we could look at something along these lines. Okay, if we compare the energy of these two, if we draw in, we do that again, this alkene, appropriately we should draw it lower than the other alkene, and that's because we have a terminal alkene there, and we have an internal here. Well, the internal is more stable because it has more things, at least the way we were talking about it in class, has more things blocking the reactivity of that pi bond. It's not strictly correct, but it works as far as we're concerned. So the internal is lower in energy. What happens as we add a second pi bond? Okay, well, as you might guess, based on how much space is on this slide, that as we add a second pi bond, so add pi, we're going to end up increasing in energy. All right, well, that makes sense. But where do we add that pi bond? Okay, so take a moment here, start with our alkene, and add a pi bond to it. Okay, and draw that structure. Once you think you've got it, go ahead and add another pi bond, or add that second pi bond, but in a different location. Okay, and once you've got that structure, try it again. Hopefully what you'll find is that there are three possible ways that we could add an extra pi bond into this structure. We could put one here. We could put one on the far outside, and we could put one immediately next to it. Okay, all of those are valid ways to incorporate that second pi bond. And due to how those pi bonds can potentially interact with each other, it's going to vary the energy, okay, of that species. We can monitor that energy difference by looking at the heat of hydrogenation. Okay, and we'll end up seeing this again in second semester when we look at benzenes, because one of the things that we'll find with benzene is that it's incredibly stable. And the reason being is much the same idea on what's happening with this. So what we're looking at is these three possible situations. And yes, I did organize these in such a way to represent their energies. Our upper right is going to be the highest in energy. We've put a lot of electron density all around that center carbon. Okay, so that carbon becomes a little bit more reactive and hence higher in energy. So we get a larger heat of hydrogenation for that one. Okay. If we go through and take a look at the other two, this guy is going to be lower in energy than that one. Okay, and we need to kind of come up with some reasons behind it. And instead of me going through and saying this guy and that guy, upper right and all that, let's just come up with some names behind this. The names that you'll see will be isolated, conjugated, and cumulated. So cumulated because we see a cumulative effect. The pi bonds are stacking pretty much on top of each other. Isolated because that second pi bond is completely independent of the other pi bond, nowhere near it. And then conjugated has to do with our favorite 9-letter word, resonance. Okay, that resonance effect lowers the energy of those pi bonds, which then lowers the heat of hydrogenation. So that compound becomes slightly more stable due to that resonance effect. Okay, so resonance is massively important to stabilization. You'll end up seeing lots of questions based both with heat of hydrogenation and resonance, and you'll also see resonance pop up as far as reactivity goes, as far as acid bases go. So you really do need a lot of practice with resonance. Okay? So lessons on this slide: resonance important, conjugated is lower in energy than isolated, cumulated is the highest in energy when we're looking at our dienes. I was sure there was something else there. Oh, trying to identify and see these. Cumulated, we've got our pi bonds stacking on top of each other. Conjugated, we're alternating. So it goes pi bond, sigma bond, pi bond. Isolated, pi bond, minimally at least 2 sigma bonds and then a pi bond, but we can have any number of sigma bonds. Okay, that could be an infinite amount of sigma bonds in between. Minimally it needs to be 2. Okay. And that's what's going to prevent those pi bonds from interacting with each other. The conjugated pi, sigma pi, you've got conjugation, you have resonance, you have a stabilization effect. So, quick sidetrack, just because I have noticed that people are still having problems with this, which is understandable. Okay, don't get too frustrated by it because it is a lot of effort to try and remember and keep these things together. Resonance and mechanisms both involve arrow pushing. And what I'm seeing a lot of people doing is just drawing the answer and then adding the arrows in to account for it. Well, that works really well if your answer is right. If you know how to move arrows and use them, you'll always get the correct answer because the arrows tell you what the answer is. The answer doesn't necessarily tell you what the arrows are. Okay? So take advantage of understanding how to move the electron density, draw those arrow pushing, draw the arrows in there, and then draw the result of those arrows. That will set you up to getting the correct answer each and every time. If you try and guess to the structure or the final answer, you're really making things up, and theoretically you'll end up losing potentially charges. Okay? And you will see a lot of formal charge kind of things pop up, so you need to know where those things are supposed to be. And you will know that by using your resonance arrows appropriately. For both resonance and mechanisms, you need to find a source of electrons. That source is either lone pair electrons or pi bonds. Either one is fine. It's not a big deal which one you pick. There really isn't a wrong answer per se. There's just one that's not right or less right. Okay? So once you've identified your source of electrons, you need to then move those electrons in a very particular fashion. Okay? The electrons, if they started on an atom, can move from an atom to a bond. And that bond will be immediately next to it. You can't just pick up atoms and throw them across the structure because they're incredibly unstable. The other way you can move, if you decided to take the electrons from a pi bond, is move them from the bond to the atom. Okay? And again, same idea. It'll be an atom immediately attached to that bond. Okay? We can't pick it up and move it several units away. There is a third way to move electrons, and this is the one that I think throws people the most for a loop, which is why it's not listed on this. That third way to move electrons is to go from bond to bond. Really, the bond-to-bond move is coming from going from bond to atom and then atom to bond. We've decided to shortcut the bond to atom and then atom to bond because usually the bond to atom move results in a charge that we could get rid of if we then do the atom to bond. So what it ends up generating is a bad resonance structure, quote unquote bad resonance structure, and we would then exclude that. Okay? And I'll show in an example here real quickly what I mean with that process. Once you've done that single arrow, you want to check and verify your octets are appropriately satisfied. Okay? The biggest issue is having more than an octet. You can have less than an octet because that'll get you charges, but you cannot have more than an octet. More than an octet is very, very bad, and we need to fix that. Right? To fix that, you will break a pi bond in the case of resonance by moving the electrons away from the atom that has exceeded its octet. Okay? Because it has too many electrons. That's why it's exceeded the octet. In the case of mechanisms, what we'll end up doing is breaking the easiest bond possible. Usually we'll break pi bonds first, then sigma bonds. Okay? If you decide after breaking that bond that that was a horrible bond to break, you just go backwards and you try again. If there is no bond to break, then you don't have a reaction. Okay? So let's take a look at some examples now. We'll start with resonance. Okay? And I do kind of want to walk you through this all the way. So we would find a source of electrons, either the lone pair or a pi bond. I'm going to pick a lone pair, and the lone pair that I'm going to start with first is on this oxygen. And I'm going to draw those electrons coming down. Okay? Because they can't go anywhere else. They can't leave the structure. We can only move them from that atom into that bond. And what I'm now about to draw is what you should be visualizing in your head. You shouldn't actually draw this out. So what we'll end up with is now a triple bond between the oxygen and our nitrogen. Whoops. I didn't touch anything else, so I'll leave everything else the same. Okay, and now that I've done that motion, I can go through and evaluate. Okay, verify that my octets are satisfied. I can check the oxygen. My oxygen is still satisfied, so I'm okay with that. I can check the nitrogen. When we go through to determine our octet on the nitrogen, it has 2, 4, 6, 8, 10 electrons around it. That is an invalid result. So now what I would real quickly do is look at this structure and say, okay, is there a pi bond that I can break? Yes, there absolutely is. That pi bond is with the oxygen. So I would go back to my initial drawing and I would move the pi bond back to the oxygen. Okay, so let's now draw that result. Okay, because that previous structure that I had there was an invalid structure, I can't show it as a resonance structure. So now I would go through, based on my new arrow pushing, my oxygen. Okay, let's see what happened. I took a pi electron, whoops, that was not meant to be an eraser. I took electrons and I made a new pi bond, so let's show that new pi bond. Whoops, again, getting a little overcrowded there. Show that new pi bond. But then I took electrons out of a pi bond and went back up to the top. Okay, oops, again. It's really hard to stepwise through this. So those were those pi bonds. So I made a pi bond, and then I broke a pi bond. So let's erase that other pi bond and put the lone pair back on the oxygen. Huh, interesting. What's the relationship now? Again, check my octets. Oxygen satisfied, nitrogen satisfied, carbon satisfied. Address formal charge. Remember, with formal charge, valence electrons. Been writing this a whole bunch lately, so hopefully it sticks with you guys. Valence electrons minus the number of bonds, minus the number of non-bonding electrons. We go through and do that on the nitrogen. You should see that the nitrogen has a positive charge. So now that we've gone through and drawn that fancy resonance, now we take a look and compare those two structures. What is the difference between those two structures? Absolutely nothing. Which means, should I draw a resonance or a quote-unquote resonance structure? No. All gone. All of that work, and we went back to where we started, square one. What does that mean? That means that the lone pair that I picked on the oxygen is not involved in resonance. Okay, that was a lot of work to find a not involved with. Okay, but it doesn't matter. That's what you're supposed to be doing with your resonance structures. You should be going through and finding that it does not work. And I'm afraid that everybody's thinking, I got to find what works. What does not work is a very good thing to find as well. So draw it out, see what the result is. Okay. Next thing I'm going to try and do, I'm going to look at the pi bond. So I'm going to take electrons from the pi bond and I'm going to move them to the oxygen. Why would I move them to the oxygen? Good question. Well, I look at where those electrons started. They're in a pi bond between a nitrogen and an oxygen. Oxygen, being more electronegative than our nitrogen, would be willing to take those electrons away. So that's a perfectly valid move. Okay. Now we'll check octets. I don't have anything exceeding an octet. I do have things being under an octet. under is kind of okay, and we'll address that in a second here. Right, but you should be able to determine that the oxygen is negatively charged and our nitrogen is now a positive 2. Okay, what is the relationship between the structures? Are they different? Yeah, they are drawn different, so that this is a valid resonance structure. Is it a good one? Heck no. Okay, we've got a massive positive 2 charge, a whole bunch of extra charge in the structure. Just in general, it's not a good resonance structure. But it is a resonance structure. Okay. Now that I've done that, I'll go through with this new structure, and so this is the nice part with resonance, is I will take a look at that resonance structure. Okay. Once I've drawn one, I can then move to the next one by moving through. So if you do a single pair of electron motion, you can get all possible resonance structures. Once you've got all possible resonance, you can start to eliminate the really bad ones. Okay, if there's really bad ones. So with this structure, no pi bonds to worry about, but I do have lone pairs. I could take the lone pairs from the oxygen, but that takes me right back to where I started, so I'll take the lone pairs from the carbon. So I'll move those electrons from the atom into the bond, and notice that my arrow is starting with the lone pair and it ends in the bond. Again, I will now go through and draw exactly what I have. Okay, and you'll notice that everything I'm drawing, at least initially, is stuff that I didn't change. Okay, because if I didn't touch it, it's not going to change. It should stay the same. I took the lone pair and I moved it into a bond between the carbon and the nitrogen. Now that I've done my single arrow pushing, I will evaluate my structure. The oxygen was negatively charged, but I didn't do anything to it, so I didn't have to worry about that. The carbon was negative, but lost electrons into the bond. It is now neutral, so I can leave it as is. The nitrogen was a positive 2 charge, but it just gained electrons by making that bond. It is now a positive 1 charge. Now that I've got my formal charges assigned, I can now compare this structure back to all the other structures. Okay? There's no invalid octets. I've got all my formal charges on there. I do have a resonance structure here. Now that I've got this structure, I could go back through and try and draw another one. I'll find that I can't, that I'm going to be stuck with these 3 possibilities. If a question was to now ask, how many resonance structures are there? Well, one option, someone might say 3, right? But the resonance structure question, or the how many resonance structures are there, is usually in reference to how many good resonance structures are there. How many structures are there of equal energy? And when we add that little clause into this, hopefully what you'll notice is that that middle one is a horrible resonance structure and is typically not counted. What we're looking at is the 2 on the outside. Okay? But how could I add arrows to my very first structure to make the structure on the right? Well, the oxygen does need to become negatively charged, but maybe in that motion I have already visualized that nitrogen started positive, doesn't want to stay positive, or wants its electrons somehow, and having oxygen take those electrons away is going to generate a very unstable intermediate that I will immediately provide electrons to stabilize it. I've now gone from beginning to end. Okay, so 2 methods to go through and deal with resonance. Well, really one method, but different ways of approaching it slightly. Okay? What happens when we look at mechanisms? Well, it's a very similar process with mechanisms. And we ran into this question when I asked which atom is the electrophile in an individual structure. Well, an electrophile must accept electrons. And if we look at this, there's no real atom that can accept any electrons. However, our carbon ends up being the most electrophilic. And for some reason, electrophilic is blue in my mind, so let's make it blue. So mechanistically, what happens? Well, the first thing I personally would do is I see this sodium and iodide and I go, that's an ionic bond, which is going to give me Na plus, and it's going to give me iodide, which is a negative charge. I know Na plus is completely non-reactive, so I'll now look at the iodide as my negative. That means I need to find something positive. Well, the most positive thing I've got is going to be that carbon attached to a chlorine. So I'll have the iodide attack that carbon. If I was to draw out the result of that, I might end up with something looking like this. Okay, and hopefully you realize that that structure has an issue with it. We had implied hydrogens to begin with. That carbon has 5 bonds. That's really, really bad. So what we do is we erase that result and go back to our starting material and say, okay, is there a weak polar bond to break? Okay, yeah, we do have a polar bond to break. We have that bond to a carbon and a chlorine. And the end result is I now end up with my iodide and with chloride floating off on its own. Did it have to be chloride taking the electrons? No, I could have picked any other atom that was attached to that. Okay, so let's go back through and try that. Okay, because remember, we want to break the easiest bond. So let's say instead that I tried to break this bond. Well, what's the result in that case? We again draw out all of our arrows. That carbon now gains an electron pair, and I'd have a carbon now with iodide attached to it and with chloride. Well, how stable is that carbanion? Oh, it's really, really unstable. So what happens? It very swiftly attacks, kicks back out our iodide, and we go right back to where we started. Okay? So the idea is to go through and stepwise evaluate. Show an arrow pushing, have something reactive, be it negative or positive. Well, it should be negative. Show that negative attack. Think about what repercussions come of that attack. Does it allow for a stable intermediate? If not, then we have to break a bond. And if there's no bond to break, the iodide gets kicked right back off and nothing happens. And that nothing happens one is a very tricky problem to deal with. And it can really only come from evaluating these charges and seeing what things shift around. Okay? So, addition reactions with dienes. So back to looking at our dienes real quickly. With two alkenes, we need to decide a couple different things. First off, which alkene is the one that reacts? And then we also have to watch out for intermediates. And as a very final caveat that might help you kind of elucidate where this is going, we've got to think about what product is favored in this. Wait a second. Nope, that was right. So if we take a look at this alkene, which alkene is going to, or which double bond should be the first one to react? Okay. Well, if we don't know, we go through and we react with both. So we could pick up our hydrogen in our red, and we end up with a positive charge here. Or we could have our other alkene pick up a hydrogen with blue, and we'd end up with either the positive or with our positive charge here. Okay, between these two, there isn't a whole lot of difference as far as the positive charge. So we might think that both are valid options. But what we should do is go back and look at the dynamics of the reaction. Okay? The carbocation is a secondary in both cases, and in both cases resonance stabilized. So what we would need to evaluate is which alkene is most likely to react. Well, as we've talked about before, that terminal is much more accessible than the internal alkene, and so we might consider that the terminal is going to react faster. That is, kinetically, the terminal alkene is going to be more likely to react, okay, because there's no thermodynamic feature in this. So kinetically, going back to speed. If we make this easier and switch to say something like this, now it doesn't matter which double bond reacts because it's going to be the same intermediate either way. Okay? And we'll end up getting our carbocation here. Now we run into another issue here. We've got to watch out for intermediates. We have resonance. Okay? That resonance is going to allow me to draw another carbocation. Okay? From both of those carbocations, I can now have the bromide attack. Okay? Or the bromide attacks here. And we end up then with two possible products. And we would now have to decide between these two possible products which one is more likely to form. Okay? So we could go through and evaluate the stability of our carbocation. The carbocation is different in energy in this case, but because they're resonance structures, they're effectively the same. Remember, we can't say one is more than the other. But what we could do is go back and look at our final product. When we look at the product, what's happening? Well, in one case we have an internal alkene, one case it's an terminal alkene. So we've got internal versus terminal. Well, the terminal is a higher in energy alkene, so we might say, oh, the terminal alkene is going to be less favored because it has a higher energy. So we could look at that as a thermodynamic favoring, because the product, our products have different energies. The other option is we can bring in this kinetic effect as well. In both these cases, we end up forming that secondary carbocation pretty much instantly, okay? Which means bromide is most likely to encounter that carbocation first. Otherwise, it would have to travel all the way around to the other side to attack the other position. So speed-wise, bromide's much more likely to encounter our carbocation or our secondary carbocation, so we might expect this one to go faster. So if we look at energy, we would expect our internal double bond to be our product. If we looked at speed, we would expect our terminal to be our product. Well, that gets a bit challenging. How do we know which product is favored? Well, what conditions control each of these things? Okay, the easiest one to evaluate would be thermodynamics. If we provide or look at a thermodynamic control, what we'd want to do is change temperatures. Okay, so let's take a look at our thermodynamic versus kinetic with something you may recognize already. Diamond and graphite are both possible carbon configurations. Diamond happens to be thermodynamically less stable than our graphite. Hence it has a higher energy, at least in this picture, okay, than our graphite. However, if we go through and take a look at the kinetics of the reaction, so our kinetics is determined on the upper part, what ends up happening? Well, according to the kinetics, it's a lot easier or faster to form diamond than graphite. So our thermodynamics would suggest that graphite is our more stable product, because we're looking at the bottom half of our diagram. That energy difference gets us to our thermodynamic effect, whereas the top part is our kinetic effect. So it's looking at the relationships between those two to decide what's happening within our reactions and how we might control those. So if we go back to our example, the very first thing that happens is that proton transfer. But then the next part is that bromide has to come in and attack. And it either attacks the carbocation directly, or it can attack the other position, which is going to result in two possible products. Okay? If we finish out the energy diagram, what we end up seeing is that for our 1,4 product, where our hydrogen was added to the 1 position and our bromine was added to our 4 position of our starting material, thermodynamically, that is a favored product. Because if we look at the energy difference between our reactants here and our final products, that energy difference gives us a much larger delta G in the case of the 1,4 product than it does for the 1,2. So that means thermodynamically we would expect that product to form first, or form in a largest amount. But if we also then take into consideration the kinetic effect, when we look at our kinetics, I can spell kinetics. When we look at our kinetics, we have a new issue. The 1,2 is going to form faster than our 1,4. So if we want to control the balance of these, what we're going to have to do is play around with the temperature to make sure or help us improve one product over the other. And that's really going to come down to our heat. If I add in a lot of heat, that's going to give me enough energy to for sure clear both of those. That excess energy will also allow the reverse reaction for the thermodynamically unstable product until eventually I can make the thermodynamically favored product. So a lot of heat helps the formation of our thermodynamics. If we remove all the heat, now I have hardly any energy in the system. Well, if there's no energy there, our reaction is going to go through the path of least resistance and will form primarily the 1,2 adduct. So what we're trying to look at is that balance between our thermodynamic and our kinetic, trying to decide how that's going to work out for us. Okay? So when working with your dienes and their addition reactions, watch out for resonance and start to consider this thermodynamic versus kinetic issue, which will again pop up a little bit later as well. And yep, that'll be in our next video. So